This is Chapter 17, Water Resources, Lecture 1. Our goals for this chapter include to investigate where water occurs on Earth. We'll look at how it moves and how we use it as a society. We'll also look at the setting of groundwater and its relationship to surface water, and we'll investigate groundwater contamination and remediation. Starting off in the Snake River Plain, southern Idaho. For context, this is north. The Snake River flows southwest, and most cities and farms are located near the river. That's what supports life in the area. Now, water from the Lost Rivers area soaks into the subsurface, and then it reemerges in the Thousand Springs area right over here. We can kind of visualize how this water might move underground and then resurface over here. Now, the Snake River Plain, it is underlain by basalt, and there's relatively recent dark lava flows at the Craters of the Moon National Monument. The Big Lost River and other drainages all flow southeast through the fault block valleys, and then they disappear when they hit the plain and the water sinks into the ground. And the largest reservoir here is the American Falls Reservoir by Pocatello, right about here. Okay, so settings of Earth's water. The oceans have 96.5% of near surface water on Earth. It's salty, of course. Rivers and streams are important sources of water and transportation of water and sediment. Lakes can be fresh or salty. Most are freshwater lakes, but saline or, say, brackish, which is somewhere between fresh and saline, are located in dry climates. Swamps and wetlands as well are settings of Earth's water. Water's on the surface in those. The atmosphere is like 0.001% of Earth's water as clouds, rain, snow. Glaciers, that has 69% of fresh water. Water's also in permafrost and ground ice in these areas. Biological water, that's water in cells and structures of plants. And then groundwater, that's 30% of Earth's fresh water. You've got water and minerals there as well between sediments. Can be a large amount. Okay, we'll look at these as the distribution of water. Okay, so most of Earth's water probably originated during the formation of the planet or from comets or other icy celestial objects. Most of this water moves to the surface over time, such as when magma releases water vapor during eruptions. Okay, so we're looking at all of Earth's water here. Oceans having most of it, and then fresh water only being 3.5%. And then the right two bars represent only the top part of the bar directly to the left. So we're breaking down the fresh water of that. You've got ice caps and glaciers being 68.7%, groundwater being 30.1%, other water being 0.9%, and then we'll go and look at surface water from that, 0.3%, and 87% of surface water would be lakes, swamps would be 11%, and streams would only be 2%. We'll think about how water moves between different settings. So when water evaporates, it leaves salt behind. So moisture in the atmosphere is fresh, and rainfall is fresh water. We have groundwater flowing onto the surface as well. Most precipitation goes into the ocean, but some evaporates on the way down. Ocean currents also move water, and of course, water can move between surface and below surface with groundwater. So groundwater can move between rivers and lakes and many other settings. So water use in the U.S. Surprisingly or not surprisingly, much of our water usage is thermoelectric power, but it can also be done with salt water. Irrigation would be 37% of freshwater usage in the United States. You wouldn't want that to be salt water because it would not facilitate growth of crops. And then public and domestic use is the next category at 12.6. Industrial use is 5.2, aquaculture 2.5, mining 1.1, and livestock at the bottom of this estimation at 0.6%. Some water used in irrigation might be returned to canals and rivers through, say, county drains in Michigan. Some can soak right back into the ground, of course. But that's an estimation. It's hard to really know absolutely where all water goes. Okay, so volumes of water used can be reported in gallons, liters, or acre feet. An acre foot is the amount of water needed to cover 1 acre, nearly a football field, American football field, to a depth of 1 foot. So we can think of it that way. It's actually like 91 yards this way, not the whole 100 yards. Groundwater. Now that is mostly found in pore spaces between grains and sediment clasts. By clasts, of course, we mean grains of sand, silt, and clay-sized particles, as well as pebbles, cobbles, and boulders. And usually those sediments are in different sizes, of course. Pores in the upper parts here are generally unsaturated, and below the pores can be saturated with groundwater. The top of this saturated zone is the water table. We can also find groundwater in fractures. These open spaces can contain groundwater. Nearly all rocks contain some fractures, but some rocks are more fractured than others. And then fractures may be the only pathways for water in some rocks, like, say, granite. Water can enter fractures that are interconnected. We see that here, kind of. More and wider fractures provide more space for water to be held. And then cavities, not fractures, but just open spaces within rocks. Limestone can have cavities. So cavities can contain groundwater as well. Caves and smaller cavities can be filled or partially filled with groundwater. But groundwater in caves is not the main way groundwater occurs in most regions. It's just something to note. If you wanted to, you could draw and label 1 or more sketches that illustrate the settings of groundwater, showing how groundwater can exist between grains, in fractures, and in cavities. So how does groundwater accumulate? We can look at all the places where water could go in this figure. Now, rain or snow can evaporate or be captured by plants. Water can flow down the surface as runoff. Water can then accumulate on the surface of the landscape in wetlands and lakes. Water can also seep into the ground, and then water can reach the water table and seep down into the saturated zone, highlighted here. And below the water table, groundwater can flow if the rocks have interconnected spaces. Okay, porosity is the proportion of open space within a unit. So which of the following have lower porosity and which have higher porosity? These are clay particles here. They're not fitting tightly together in this instance. They're these flat particles. It has high porosity. We can see all that void space. Now this is granite. The crystals here fit together tightly. They're interlocking. There's very low porosity here. Water's not going to move through that very well without fractures. And with this jar, we have rounded, fairly well sorted clasts. They don't fit together tightly, like a jar of marbles or something like that. That has high porosity. This jar has sand to fill in that void space. And it's poorly sorted because there's a huge range in grain size, and it fits together more tightly, so it's lower porosity. Now, permeability, that looks at how connected, or that reflects on how connected pore space is so that water can flow through a unit. So which of the following have lower permeability and which have higher permeability? This is granite with many fractures. It seems to be well connected as well. It's got a higher permeability than, say, a compacted clay. Everything is, pushed down together. That could later form shale. Low porosity, low porosity and low permeability, if not fractured. And then we have these loosely cemented gravels, high permeability, well-connected pore space, and then a porous volcanic rock with isolated pores. That's low permeability, although it probably has high porosity. The pore spaces are not well connected, so water cannot flow through this all that easily. Okay, let's talk more about the water table. We'll observe how the water table interacts with topography. The water table has a similar shape to the land surface, but it's more subdued. Groundwater flows down the slope of the water table, and the shape of the water table is mostly independent of rock units, but rock types will influence how fast the water flows, if at all. So that relates to porosity and permeability. This looks like high porosity, and the pores seem to be pretty well connected. So I'd say the permeability is pretty high too. Okay. Slope matters as well. A steeper slope will equal faster flow. If we're comparing, say, the same types of materials, steeper slopes will make water move faster than gentle slopes, like this. So you could also have flow in different directions within an area if groundwater is divided due to these topographic differences, right? So we have flow this way and we have flow this way due to the landscape itself. Additionally, you could see on the other side of this hill flow going down in the opposite direction of this arrow. We call that a groundwater divide. Major types of aquifers we can define as unconfined versus confined. So an unconfined aquifer is open to the Earth's surface and to infiltration of surface water into that aquifer. And a confined aquifer is overlain by less permeable materials. And let me back up here. What is an aquifer? Well, there are legal definitions for this, regulatory definitions that I use in my day job, but what it is a saturated zone of water that basically stays in the same place for quite some time consistently over the years. Regulatorily, we might say that it's a usable amount of aquifer and it doesn't dry up. Okay. So We can also have a perched aquifer where perched water sits above the main water table. So you've got a water table down here, and then the aquifer, this lens of saturated material, is right above. You can also have an artesian aquifer where water rises in a pipe, maybe to the surface, due to differences in pressure. So how does water move between the surface and the subsurface? Water can soak into the surface, of course, and become groundwater. Precipitation, snowmelt, and surface water can soak into that subsurface, right? The water table is generally below the surface, so water seeps in. But where the water table intersects the surface, again, the water flows out, like in this lake. All right. So how are lakes and wetlands related to groundwater? We'll look at the settings of lakes and compare that to a water table. We've got a lake that's perched above the water table. It's actually giving water to the subsurface, which flows down and intersects and supplies this body of water and further flows down slope into this body of water. Wetlands can be at the water table or perched. Kind of depends on, say, the supply of precipitation as well. We can call this a topographic bench and this a valley bottom. So how do streams interact with the water table? Okay. This stream is actually lower than the water table, so it gains water over time from the water table. This stream is higher than the water table, so it loses water. It's probably fed then by precipitation or runoff from somewhere else. All right, it's a little less stable that way. You can have a mound of groundwater below the stream from water flowing into the subsurface. And we'll stop here for today.